Welcome, guys. This is 3.3, future value of annuity and sinking funds. Okay, so we've been doing simple interest theorem, and then we did compound interest and continuous compound interest. So now we get into annuities. So a couple of definitions right below. An annuity is a sequence of equal periodic payments. An ordinary annuity is one in which payments are made at the end of each time period. The future value of annuity is the sum of all payments plus all interest earned. And the present value of an annuity is its current worth. Okay, today we are just going to be doing future value. Okay, so what future value means is, all right, well, let's say we want to have, what is it? We want to have X amount of money in the future. Well, how many payments a month must we make to have this future value of money in the future? So that's what this is about. This handles payments and future value. So every time you make a payment, there's a payment plus interest on the next payment, plus interest on the next payment, plus interest on the next payment. We can calculate it one by one, or we could use this lovely formula that sums everything up, which is right here. Future value equals payment. Future value equals payment times 1 plus I to the n minus 1 over I. This formula will sum up all the payments you make. I mean, it has to be an equal payment. Will sum up all the payments you make to give you that future value amount. Okay, so this is the formula we will be using. Okay, so to go over some stuff, before we get started, let me see. So for the formula, you see you have I and N in there. You have I and N. Well, remember that I, just like in compound interest, it's still R over M, rate over compoundings. And just like compound interest, N is still compoundings times time. That's it, where time must be in years. Okay, so that's what I and N still represent. Okay, and this says, if the account begins at 0 and equal payments are made at the end of each period, the amount in the account, the future value, and the payment are related by the following formulas. Okay, so what you see below is the first one, which is the future value formula. Future value equals our payment times 1 plus I to the n minus 1 over I. So this is if we're given the payment, we're given the compoundings, we're given the rate, we're given the time, we plug it into this formula. Okay, and to save us some time, well, the second formula is if you're solving for payment. So we have already rearranged it for you, so we don't have to go through the rearrange this formula process. You're welcome. So if you're solving for payment, we will use the second formula. Payment equals future value times I over 1 plus I to the n minus 1. Okay, and then let's say we want to solve for n. Well, by the use of natural logs, we now have n, the very last formula there. N is equal to the natural log of future value times I plus payment minus the natural log of the payment over the natural log of 1 plus I. Ooh, so we didn't have to spend time rearranging on it. So lucky you, all you have to do is know these three formulas, know how to use them. And these are for future value, right? Future value. So an amount of money you want to have in the future. Okay, perfect. So the next three examples are going to be working with these formulas. So they're going to give us the pieces. So we want to find the appropriate formula. Okay. So example 1, they give us that, let me zoom in a bit. How's that? Example 1, they give us that N is 25, I is 0.04, payment's 100. What is the future value? This means we will be using the very first formula there. Future value equals payment times 1 plus I to the n minus 1 over I. Ugh, I know it's a lot. All right, I'm going to write it on the example down below, so give me a second. So we will be using future value equals payment times 1 plus I to the n minus 1 over I. Okay, now let's go down. That formula should be there. Just making sure it's right. 1 plus I to the n minus 1 over I. Okay, perfect. Now they're giving us all the pieces, so let's just go ahead and plug it in. So we get future value is equal to the payment of $100 times 1 plus I, which is 0.04, raised to the n, which is 25, minus 1. And all of this is over I, which is given as 0.04. Okay, which means let's go ahead and type it in the calculator. All right, how do we type this in the calculator? Well, let me come back to this one, just the regular TI-30XS. All right. Okay, so the way to type this in is I'll start with 100, and then I'll hit times fraction, parentheses. 1 plus 0.04 is just 1.04. Raise that to the 25th, minus 1. Then put it all over 0.04. Just like that. That's it. Just like I wrote it over there. And hit enter. So this says if we're making $100 payments at an interest rate of 0.04 for, what is it? We don't necessarily know the compoundings. We could find them. So we could say for 25 months, right? This would be, we would have $4,164.59. There it is. Okay. Let's say you didn't have a fancy schmancy calculator. How would you type this in? Oh boy. I would type this in as, what would I start with? I'd start with parentheses and I'd say 100 times 1.04 raised to the 25th minus 1. Close that whole parentheses because that's in the numerator. Oh, I might need another parentheses because that 100 would have to distribute. So, oh boy, yeah. So I think I would put another parentheses in here. Then, would that close it? I think so. 100. Yes, okay, cool. And then I would divide all of that, or maybe it closed it. I think I need one more. Let me see. Divide all of that by 0.04. Bam. 4,164.59. That is like classic input that you can put on a graphing calculator or just a normal calculator. Awful, I know. Okay, perfect. Let's keep moving. All right. So now we're going to come to example 2. And for example 2, they give us future value is 2,500, n is 10, I is 0.08. What is the payment? So now we are looking for the payment. So we're going to use the second formula that's up here. Okay. So I'll write it down below. So again, give me a second. So payment equals future value times I over 1 plus I to the n minus 1. I over 1 plus I to the n minus 1. Okay. Now come down here. There's the formula that I wrote. And let's solve it. They're already giving us the pieces. So let's solve it. So we get payment equals the future value of 2,500 times I, which is 0.08 over 1 plus 0.08 to the n power, which is 10 minus 1. 1 plus 0.08 to the 10th power minus 1. Okay, now we have all the pieces where they need to be. Go ahead and calculate. Okay, so here we go. Clear this out. 2,500 times fraction button 0.08 over 1.08 raised to the 10th minus 1. Make sure that 1 is not in the exponent. There we go. Okay, hit enter, and we get that the payment should be $172.57. There we go. Okay, not bad. All right, so which means we can move on to number 3. Future value is 8,000. I is 0.04. Payments 500. What's the value of n? Which means we are going to use the third formula over here. There we go. So I'll write that down below as well before continuing. So we get n equals the natural log of future value times I. Oops, no parentheses. Plus payment minus the natural log of payment all over the natural log of 1 plus I. All right, FV times I plus payment minus natural log payment, natural log 1 plus I. Okay, perfect. Now I'll scroll back down. There's the formula. Okay, they're giving us all the pieces. Let's plug them in. So n equals the natural log of future value, which is 8,000, times I, which is 0.04, put times 0.04, plus the payment of 500. All right, minus the natural log of 500 of the payment. Okay, and all over the natural log of 1 plus I, which is 0.04. Okay, which means we are now ready to type this in the calculator. So here we go. I'm going to do fraction button, natural log, 8,000 times 0.04. Make sure we don't forget any zeros, plus 500. Minus the natural log of 500 over the natural log of, that just becomes 1.04. There it is. Enter. We get 12.61. Okay, awesome. And there, that's how you use your formulas. Okay. Let's move on. Now we get into actual word problems. All right. No. Very good. Okay. Example 4. USG annuity and life offered an annuity that pays 7.25% compounded monthly. If $1,000 is deposited into this account annuity every month, how much is in the account after 15 years? And how much of this is interest? Okay, so we have to know what formula to use, but first let's get the pieces, right? Let's see. Okay, so what are they giving us? They're giving us that the rate, so an annuity that pays 7.5% compounded monthly. So the first thing they're giving us is I. Remember that I is rate over compoundings, which means that you get the rate of 0.0725 over our compoundings. We are compounding monthly, so that is 12. Okay. No, I doubt that this is a nice number. So let's see. Let's try it out. 0.0725 over 12. And yeah, I'm going to leave it as a fraction. Okay. And then the next thing they're giving us is that $1,000 is deposited every month. So the next piece of information is that our payment is $1,000. Okay. And then it says, how much is in the account after 15 years? Okay, so that means they're giving us N. N, remember, is M times T. So compoundings times time. So M is 12, because we're compounding monthly. Time is in years, so that's 15 years. And what's 12 times 15? Is it 180? Yes. So we get 180. Okay. So this means that if we have I, we have payment, we have N, this means we are looking for the future value. So we will use the future value formula above. And I'll write it again for this problem. So future value is given by payment times 1 plus I to the n minus 1 over I. Payment times 1 plus I to the n minus 1 over I. Okay, there's our formula. Now let's use it. Maybe I could zoom in a little bit now since we have all the pieces. There we go. How's that? Okay. So we put all the pieces in, and this means that future value is going to be 1,000 times 1 plus, and I'm not converting I into a decimal, so this is going to be 0.0725 over 12 raised to the n, which is 180, minus 1, all over I, which is 0.0725 over 12. Okay, and now let's type that in our calculator. Future value okay, so clear. Just like I wrote it, 1,000 times fraction button, parentheses, 1 plus, I'll hit the fraction button again, 0.0725 over 12, close, raise it to the 180, minus 1. Over, I don't need parentheses, I just wrote it there, so you saw everything nice and separated. So here I can just hit fraction button again, 0.0725 over 12. There we go. It's all typed in just like I wrote it. Let's hope we didn't forget any zeros, and enter. $323,943.07. So that is the future value of your annuity if you are depositing $1,000 every month for 15 years and your money is compounded monthly, meaning your money is getting interest every month for 15 years. So this is your money after 180 months or 15 years. Not bad. These are better than the other problems. Okay, so we wanted to know how much of this is interest. So I can do that over here. Let's see. There we go. So how much of this is interest? Well, we're making $1,000 payments, right? We're making $1,000 payments for 180 months, right? Times 180. Keep scooting over. There you go. So 1,000 times 180. It's 180,000. So this means we've put $180,000 in 15 years. And at the end of that 15 years, we get an annuity of $323,943. So I'll put that above. 323,943. I'll leave the 7 cents out, unless you really want it in there. So subtract these two amounts. So 323,943 minus 180,000. This means that we've gained $143,943 in in interest. Now that's some interest I like to make. Interest earned. There you go. Not bad. Okay, awesome. There it is. That's how we set these problems up. Label all the pieces and figure out what formula you need to use. Okay. Example 5. A self-employed person has a retirement plan. If deposits of $7,500 are made each year into an account paying 8% compounded annually, how much will be in the account after 20 years? So again, this looks like it will be future value. Okay. So let's set up the pieces again. All right. So what they're giving us first is the payment. They're giving us that we are depositing $7,500 each year. And then they're giving us I. Remember, I is rate over compoundings. So we are paying 8%, so 0.08 compounded annually. Well, how many years are in 1 year? That's 1. So this just becomes 0.08. Okay. And then they are giving us N. N is compoundings times time. And we are compounding annually for 20 years. So 1 times 20, we get 20. So again, this is the future value problem. So this should be future value equals payment times 1 plus I to the n minus 1 over I. Did I get that right? Let's see. 1 plus I to the n minus 1 over I. There we go. We have all the pieces. Plug them in. Future value is 7,500 times 1 plus 0.08 raised to the 20th minus 1 over I, which is 0.08. Okay, there it is. Everything we need. Future value. Type it in the calculator. Clear all this out. Okay. 7,500 times fraction button, parentheses, that just becomes 1.08. Raise it to the 20th. Move this over, minus 1. All right, and 0.08. Okay, enter. So after making yearly deposits of $7,500 for 20 years at 8% compounded annually, we will have $343,214.73 in 20 years. I like that. That's not bad. Okay, awesome. So those were 2 future value examples. Not bad. Again, label everything, know what formula to use, and learn how to type it in the calculator. Let me show you something on the calculator side real fast. So when you're typing in these exponents, right? I said raise it to the 20th. After that, you want to push this little right arrow so you get out of the exponent. If you don't, then you're going to make the mistake of doing 20 minus 1. And that is all in the exponent. We don't want that. So make sure that you move that over like that. Okay, very easy mistake to make. So just watch it. Okay, perfect. All right, next one. All right. Example 6. The Hartford offered an annuity that pays 5.5% compounded monthly. What equal monthly deposit should be made into this annuity in order to have $100,000 in 10 years? So this is going to want to look for payment because it says what equal monthly deposit should be made. So again, let's go ahead and list everything that we have. All right. So we'll start with what it's giving us first. It's giving us I. So I is rate over compoundings, and our rate's 5.5, so 0.055 over compounding monthly, that's 12. And again, I doubt this is a nice decimal number. Let's see. If it is, we'll use it. Nope. So it's not. Leave it as a fraction. And then it says, what equal monthly deposit should be made into this annuity in order to have $100,000 in 10 years? Okay. So they're giving us the future value that we want. We want to have 100,000 in 10 years. And then the last piece they're giving us is N. N is compoundings times time. We are compounding monthly, which is 12, times the years, which is 10. So that's 120. Okay. Now, we know what formula to use. We will be using payment equals future value times I over 1 plus I to the n minus 1. Let me make sure that's correct. Let's see. Yes, future value times I over 1 plus I to the n minus 1. We're good. Okay, now let's plug everything in for the payment. So you'll get payment equals our future value of 100,000 times I, which I'm leaving as a fraction, right? Ew, that's an ugly 100,000. Let me see. One moment. $100,000 times I, which is 0.055 over 12. Put that in parentheses just to make everything nice and neat. Over, what do we have? Over 1 plus I. So parentheses 1 plus 0.055 over 12 raised to the 1/20th minus 1. There you go. Let me zoom in on that. There you go. Okay. So that's how we're plugging this in to the calculator. So next is just what is our payment? What's our payment? Okay, so clear, and here we go. 100,000 times fraction button again. 0.055 over 12 over parentheses 1 plus fraction button 0.055 over 12. Close parentheses, raise it to the 1/20th minus 1. There we go. It's all in. Fingers crossed. Boom. We get that our payment should be $626.93. So to have $100,000 in 10 years, compounded monthly, so you are making monthly deposits of $600 for 10 years. Oof, it's a lot. All right, but that's how you get $100,000 really quick. Okay. Excellent. So there's that. That was an exercise with solving for payment. Okay. Next is something called a sinking fund, right? A sinking fund. Oops, too far. A sinking fund is basically your rainy day fund, right? This is the account you put money aside for in case your tires go flat, you need to buy a new car, you need to buy a new computer, you need to buy something, right? So that's what a sinking fund is. So it's an account established for accumulating funds to meet future obligations or debts. All right, kind of like a savings account, but a savings account with more interest. All right, sinking funds are money you set aside each month to pay for quarterly, semi-annual, or annual bills. It is sort of your own escrow account that you set up for yourself when an irregular bill comes up, you aren't scrambling for money. They are designed to keep you financially afloat when something occurs that needs a bit more money than you brought home from your paycheck. Basically, they keep you from sinking financially. Like Trump bucks. Yeah, sure. Okay. So, I mean, you can definitely click that link to, I hope it still works, to see how to set up a sinking fund, or just Google sinking funds and also Google escrow. Because no matter how much I read about escrow, I still don't understand escrow. I know escrow is an account set aside by my mortgage company that collects money to help pay for property taxes, state taxes, and my home insurance. That's what I'm understanding escrow. And for some reason, escrow goes up every year because property taxes go up every year. So that's something else. Okay, but yeah. So even though if they explain escrow to you, you still don't understand escrow. Okay, perfect. So example 7. A company establishes a sinking fund for upgrading office equipment with monthly payments of $2,000 into an account paying 6.6% compounded monthly. How long will it be before the account has 100,000? Ooh, so now we're solving for time because this problem said how long. So we're looking for time. So this means we're going to use the third formula, but let's piece everything together first. So we are first making monthly payments of $2,000. So that's what I'll write down first. So first off, my payments are $2,000. And then this is getting put into an account paying 6.6 compounded monthly. So they're giving us I. I is R over M, and our rate 6.6, so 0.066 over, we are compounding monthly, so 12. Is this a nice decimal? Please give me a nice decimal for once. And wow, look at that, beautiful. So we can actually use this as 0.055. Finally, a nice decimal number, which will make the calculations easier. Okay. And then it says, how long will it be before the account has $100,000? So they're giving us the future value of what we want, which is $100,000. This means we are solving for n. We're solving for n. Okay, perfect. Which means we need the formula for n, which, let me go look at it, because that's the big one, right? There it is. I'll write it. N equals the natural log of future value times I plus payment minus the natural log of payment over the natural log of 1 plus I. Natural log, future value times I plus payment minus natural log of payment over natural log of 1 plus I. Okay, perfect. Let's get back to the problem, which I have right there. Okay, we have all the components. There's that. Let's go ahead and plug them in. So n equals the natural log of 100,000 times I, which is 0.055, plus payment, which is 2,000. Minus the natural log of our payment, 2,000. All right. Now, all of this is all over the natural log of 1 plus 0.055. 0.055. Okay. This means that n, now let's type it in our calculator. Fraction. Oops, no, not two fractions. Fraction. Natural log. 100,000, right? 5 zeros times 0.055 plus 2,000 minus the natural log of 2,000 over the natural log of 1.055. Enter. All right. This will be 24.69. So this will be in 24.69. What is that? Months? Yes. So I think my math lab may want you to round up or round down. So this could be 25 months. All right. Also, something to note if it asks you is that, remember that n is also m times t. So if we bring our answer back, that n equals 25, Well, this becomes MT equals 25. Well, we know the number of compoundings, which is 12. So this becomes 12T equals 25. And if you divide by 12, this will give you the time in years, just in case it asks. 2.25 divided by 12, 2.08. There it is. All right, so that would be or maybe just 2.1 years, or just 2 years. So that's in case it asks you for time in years. But here, if it just says solve for n, then you just put what we got the first time, 25 months. That's it. Okay, now that was an application that involved n. Perfect. All right, which brings us to the last problem. Woo! Okay, right there. You wish to save money for your child's college education. You start depositing $900 each year into an account that earns 8.1% compounded annually on your child's 3rd birthday. On your child's 17th birthday, you make your last deposit of $900, which would be 15 equal deposits in all. With no additional deposits, the money in the account continues to earn 8.1% interest compounded annually until your child is 21. How much is in the account on your child's 21st birthday? Okay, so this is going to involve future value, and this problem is also going to involve compound interest. The reason it involves compound interest is because we stop making additional deposits. So now that money just sits there and just starts getting interest. So the first thing we're going to have to do is find future value, because we want to know how much is in the account after the 15 equal deposits. So after 15 years, right? 15 deposits, 15 years for depositing that money every time on your kid's birthday. Okay, so we can make this in steps. Let's say step 1. Find future value. Find future value. So let's get the pieces that it's giving us. So let's see, we are making $900 deposits each year. So that is a payment. So payment is 900. And then it says we are getting an interest rate of 8.1% compounded annually. So they're giving us I. I is R over M, and our rate is 0.081 over our compoundings annually, which is just 1. So this just stays 0.081. Then we want to solve for n next. N is m times t. M is the number of compounding, so we are compounding annually, so that's 1. Times, well, from our child's 3rd birthday to the 17th birthday would be 15 years. Yes, 17 minus 3 is 14, but the reason we include 15 is because we make a deposit on the actual 3rd birthday. So we've made 15 deposits in all. We don't want to lose a year. So that would be 15. So n is 15. Okay. So all we need now is what is the future value, which means we can bring in our future value formula. I'll write it each time. Why not? Future value is going to equal the payment times 1 plus I to the n minus 1. Oops. to the n minus 1. Nope, see, don't make that mistake. To the n minus 1 over I. All right, just a quick check and make sure that's the right formula. Sorry, we don't want to mess anything up. Payment 1 plus I to the n minus 1 over I. 1 plus I to the n minus 1 over I. Okay, now we have all the pieces, plug them in. So we get future value equals 900 times 1 plus 0.081 to the 15th minus 1 over 0.081 over 0.081. Okay, and let's type it in the calculator to get our future value. To get future value. Okay, so 900 times fraction, parentheses, that becomes 1.081 raised to the 15th minus 1 over 0.081. Enter. Your child will have $24,627.93 when they start college. Let's hope they go to community college first, because that'll pay for community college, hopefully in the future. Or let's hope they get a scholarship, and guess what you can do with that money? You take it back. You're like, I didn't save any money for you, kid. This is mine. Okay, so you'll have basically almost 25 large for your kid on their 17th birthday, but now we're gonna let it sit until they're 21. So now here's where compound interest comes in. So where can I fit that? Just make another column over here. Sure, we'll make this step 2. 2. Find compound interest. Okay. So compound interest, remember, is given by A equals P times 1 plus I to the n, right? A equals P times 1 plus I to the n. Okay, so we want to know what is the final amount after this money sits for how many more years? 4 more years, right? Because we stopped making deposits on the 17th birthday, and we want this money to sit until the child is 21. So that is 4 years. Okay, so let me zoom in a bit. So again, we want to list all the pieces that we're using here. So they're giving us the beginning amount, P, and the beginning amount is what we've ended up with, right? P was the, how much did we make? We made 24,627.93. 24,627.93. So that's what we made after investing for the 15 years. And then it's still getting, let me see. This problem says, oops, keep going back and forth. Okay, so this problem says that with no additional deposits, the money in the account continues to earn 8.1% compounded annually. So again, I is going to be just like I for number 1. It's going to stay 0.081 because that rate hasn't changed. And then N, that's going to change because, well, first, we're still, remember, it's m times t, which means we're still compounding annually, but now the only years left are from the child's 17th birthday to their 21st. So that is 4 years. Okay, there you go. You have all the pieces, so let's plug them in to compound interest. A equals 24, 627. I keep writing 7 first. 627, 93 times 1 plus 0.081 raised to the n, which is just 4. Which is just 4. Okay. And if we let this money sit for 4 more years, the kid gets more money for school. So let's see. We get 24, 6, 2, 7, 9, 3 multiplied by 1. That becomes 1.081 raised to the 4th. Enter. Ooh, nice. So if we let that money sit for 4 more years at that interest rate, our kid will now have $33,630 and basically 30 cents. There it is. Much better. Okay, that is calculating future values, right? We take a payment, we keep putting payments in, and this formula will tell us how much money we'll have in the near future or in the far future. If we're doing it for 10 years, 20 years, 30 years, we just know that this is way better than doing compound interest. This is why I say when you invest, you just don't put one chunk of change in, you keep adding on top of that chunk of change. The more you put in, the more you'll get back. Unless the economy collapses and we get zombies. Okay, that is it, y'all.